Computer systems test then. End of term 1 in year 9 is very straightforward. There's not any tricky questions in it. The first question that you are going to be asked is on different input, output and backing storage devices. So make sure you know at least 3 of each type. And yeah, very easy first question to start off. The next question is going to ask about RAM and ROM, what they stand for and how they are different. So remember, one's temporary memory that is used to store programs whilst they're being executed, and ROM is a permanent memory used to store programs on a long-term permanent basis. For example, the bootstrap part of the operating system has to be a permanent memory so that it can't ever be changed. You're going to be asked the difference between sequential and direct access memory. So just remember that sequential must go through every single memory location in turn to get to the one it requires, whereas direct access can just skip directly to the memory location it requires, and most modern back-end storage operates in that fashion. It's a bit older, the sequential access. We're going to be at the Caesar, shift cipher and encryption, and you're going to get asked a question on whether shifting by +7 is more secure than shifting by 2 different values. So I'm not trying to give away the answer to this one because it's a problem solving question. So basically the question could be summarised by, is a shift of +7 more or less secure than a shift of -2 followed by a shift of +9? So I won't explain that one anymore, but what you can do is use a diagram to help explain your answer for that one. I'm going to be asked about why an unauthorized person can't access encrypted data. So just remember, they can actually open and read the file, but in your explanation you should make reference to the fact that they can't read it, they can't be understood unless we have a key. We're going to be asked about the different types of compression. So literally we're going to be asked for the definition of what compression is. I'm not going to explain that, but we're going to be asked a problem solving question on why important documents should be sent using lossless compression. So if you're thinking about really important photos, really important documents, we don't want them to change, we want them to appear as the originals were. So think about some advantages why we should use lossless compression in that example. We are going to be asked about RLE, so you'll need to know the definition for it, and we might have an example where we have a string of text and we get asked how it would be represented. So for this one, an acceptable answer would be to provide a count of how many each object or colour in this matter appears, and then write down the number of times it appears with the colour. So that would be an example for that one. Not a good example to show how it works though, not a good example to show how it can save on data though, because this one doesn't save a lot. So in fact this would be an example you could use to show when RLE is not actually beneficial. We're going to be asked how to complete calculations of file sizes. Now remember, we do the length times the breadth times the resolution, which is usually given in dots per inch, multiplied by the colour depth. Or we might be given the length in pixels already, so a better explanation for it would be the length in pixels multiplied by the height in pixels multiplied by the colour depth. Now hopefully you remember that the highest colour depth we're going to deal with is 24 for true colour. We're going to be asked about 2's complement and why it's better than signed magnitude representation, which was signed bit. So if you remember, and the only help I'm giving you for this one is we looked at this number and we looked at this number and we said that they were similar, maybe, is the hint I'll give you. Hopefully you could remember what I'm talking about. And the other reason that it's not great is to do with what we do with this number and to do with addition, subtraction. We are going to be asked about how to do 2's complement numbers. So we might have a number that we represent. So in this case we have 1, 2, 4, 8, 16, 32, 64, 128. So if we quickly add this up, we get 130, 194, 210. So I hope my maths is correct, and this is 212. And if we want to work out what minus 212 is, we firstly represent the number. In fact, forget this example, it's too silly an example. Let's a better 2's complement example again. Let's just go for minus 56. Let's not do minus 56. And when you do the test, you'll see why not to do minus 56. So let's do minus 48. So we've got 1, 2, 4, 8, 16, 32, 64, 128. Excuse the writing. So we want to get 48 represented, which is 0, 0, 1. And 32 and 16 is going to give us the 48, so this one should be nice and straightforward. So we write the number down normally, and then we invert all the bits, and then we add 1. So giving us 1 plus 1 gives us a 1, 0 with the carryover. Another 1 plus 1 gives us the carryover. 1 plus 1 gives us the 0 with the 1 carry, 1 plus 1, 0 with the 1 carried, 0 plus 1, and no carryover. And then this would be our answer. And we could do the cheat to check it works by doing minus 128 plus 64 plus 16, which I hope works out correctly. The trick for most people, and it's broken down, is how sound is stored in digital devices. Now remember, we have a microphone. There's a nice drawing of a microphone, which involves an analog to digital converter, which is repeatedly sampling, which is measured in hertz, and it's converting the analog signal to its equivalent binary value. Now, if we only had 4 bits for our sample depth, then we couldn't store a lot of information about each recording, whereas if we increase that sample depth, we could be a lot more accurate with the digital representation of that sample. And obviously, having 4 bits versus 8 bits, with the 8-bit, it's obviously going to take a lot more memory to store each sample, therefore the sound file will be in a greater file size. But the trade-off of that is the sound quality is better, which is another question we're going to get asked. We are going to have a question, cloud versus local storage, which is going to be probably a tricky one, so just try and think of the differences between the two. So cloud, you can access it anywhere, you have an internet connection. Local is only on the device that you require, and on the cloud, the company performs the backups. They look after it for us, whereas on a device, it's down to you to perform the backups yourself for your own files. We're going to be about different features that we can compare input, output, and backend storages on. So think about things about the processor. We know about the speed of the processor, how many cores it has, how much cache memory it has. We're going to be asked about camera, so think about resolution, and think about the capacity of storage in there. Capacity is one that applies to just about every device. We've also got access speed, which can be applied to the processor as well. And for most other ones, if it's a scanner, camera, resolution's good enough. Data transfer speed for all devices is a good one to compare them on. We are going to be asked about ASCII and Unicode, so I won't give much detail. Suffice to say ASCII 7 or 8, and we'll say Unicode. The number we want is 16. Hopefully we can all get that right. And we need to think of one more advantage for ASCII and one advantage for Unicode, and what are they? And then there'll be that asks us to write an expression to explain how many bytes are in another file size representation. Try not to give away the answer here though. So for example, if I said 2 to the power 10, we would know that was an expression to represent how many bytes are in a kilobyte, so it would be useful if you knew all of those.